Log on, tune in, find out. Another good idea from Cambridge.
Bertram was going to talk on birational models of the Hilbert scheme, etc.
Etc. Thank you, and I'd like to thank you very much, Peter, for the invitation. I'm enjoying the 6 weeks away from responsibilities. It's very nice. Okay, so let me start with sort of a question. So let me start with an arbitrary smooth projective surface. So we now know that the stability manifold of S, which I'll describe in some detail later, but it's a complex manifold of Bridgeland stability conditions on the derived category coherent sheaves on S. We now know at least that this is not empty. We don't know this for threefolds. It'd be nice if we knew this for Calabi-Yau, but we don't. We do know that this is non-empty. And what we also know is that if I fix the Chern character, let's say, for simplicity, let me fix the Chern character of a Birational-stable vector bundle. Or yeah, let's just say it's a Mumford, doesn't matter. A stable vector bundle on S, and let's also assume that it's a primitive class. Then we get a wall and chamber structure. So there's the stability manifold of S. We'll get some kind of and this is not meant to be, a closed manifold. We get some kind of wall and chamber structure. On the stability manifold, with the property that when I have a point in a chamber, then by, I guess, it's a theorem of Toda that the moduli of Bridgeland-stable objects associated to this point, this stability condition, which is what a point in the stability manifold, that this is some kind of a proper, I guess it's a proper Artin stack or something, and I think it should be finite type. And so I think the natural question, especially if you want to link this sort of up with birational geometry and whatnot, is there are a bunch of questions you could ask. First question you could ask is, and there's a sort of a distinguished chamber in which, and that's why I picked the class to be the class of a stable vector bundle, in which this is actually the moduli of Birational-stable sheaves with the given invariant. So actually I drew my walls badly, sorry. I don't want to imply that there's a single wall. Anyway, so here, there's general x's. So there's a lot of interesting questions you can ask about this. The first is this one, which is a little bit irritating. We don't. Are these projective? If you're more, it's expected that as you're crossing walls, should correspond to some kind of birational. So a birational morphism, a birational map between the moduli spaces. So I guess you could be even more audacious and ask, are these in some sense related to the minimal model program? In fact, let's be as audacious as possible and ask, is there a map? Is there a map from the stability manifold of S to, let's say, the effective cone of the moduli of Giesecker stability conditions, of moduli of Giesecker sheaves, stable sheaves, that is there, that explains all the wall crossings? That would be really nice. That would be the nicest picture you could get, I guess. And I guess the answer to all these questions is yes in the case of the Hilbert scheme of points on P2, and I want to explain that. I suspect it's also yes for moduli of stable bundles on P2 in general, but we don't have. I don't know that. So let me. This is wide open. I mean, I'm not implying any of this is known. We have a few examples for when S is a K3. By the way, the full stability manifold is basically known by Bridgeland for K3s and abelian surfaces, and but Arend and Emanuele really understand this, I think, for P2 when S is P2. Okay, there's local P2, but I think the P2 case isn't too much harder.
Although you get on to the special case, the general case where it's the polarization here and here.
Yeah, the polarization on the surface.
Yes.
Yeah, I'm gonna. Yeah, there's no doubt that the polarization on the surface will play a role. Yeah, but I'll.
We're going to be on P2. We're going to be on P2.
We're having free on P2, so I don't worry too much. Yeah, I'll explain a little bit where polarization comes in, at least for our constructions, in a little bit later. Okay, so Hilbert scheme, endpoints in P2, which I guess I'll be writing it a lot, so I'll write it as P2 bracket n. Let me remind. So I want to think of this as a moduli of ideal sheaves. So these ideal sheaves of subschemes of length n, they have the rank 1, first Chern class 0, second Chern character minus n. I always like to work with the Chern characters. The Hilbert scheme has a map to the nth symmetric power, and this gives me exceptional divisor for the map, and then it also gives me class which I'll call H, which is pi upper star of the symmetrized O1. These are these generate Picard over Q. I think E is divisible by 2. That's not going to matter to me much. But these generate the Picard group, and so over Q. And so I can draw my picture of the effective cone. column of effective divisors on the Hilbert scheme. So this is in the E and the H direction. So H is obviously one extremal ray corresponding to the contraction. And then I have a series of chambers followed by a final ray. I guess the thing to remember, I think this is right? This is a Mori dream space. I always love, which means that you only expect that there are only going to be finitely many chambers and walls. And so there's a picture, so if I let, there's a corresponding picture of birational models. Let's see, so I have X naught, which is the Hilbert scheme, mapping down to, I'll call the X's the chambers and the Y's the varieties corresponding to the walls. So I have this bunch of birational maps between models of the Hilbert scheme, followed by, I guess, a final contraction down to some variety. That's could either be divisorial or vibration. Right. So it's kind of easy to get started. So we've kind of so I should say at this point what I'm going to talk about is joint work with Daniele Arcara and Izet Koskun. So Izet has worked out all of these birational models for n up to 12 or so, just so that we could check. I imagine the first one is pretty obvious if you've thought about what it means for points in the plane to be in special position. Obviously, the most special position for endpoints on the plane would be for endpoints to lie on a line. So this first contraction would contract. Well, this would be a flip. I'll just call it. This is the flip across endpoints on a line, which means that you can, if endpoints happen to be on a line, and you contract that down to the line. So there's some exceptional set in here that's contracting to P2 dual, and then there's a flip to another side, and that's what the x1 would be. You'll have n minus 1 points on a line. You'll have some smaller and smaller number of points on a line. You'll eventually get points on a conic, and then actually you're going to get some other interesting flips that I want to describe in terms of moduli of complexes a little bit later. But anyway, so there's this picture of birational models, and I kind of want to map this up. The idea is to sort of compare this with the Bridgeland moduli space, which I need to talk a little bit about now. So does this sort of okay? I don't know. I've got this Hilbert scheme. It's got a bunch of birational models which correspond to moving along the crossing walls in the ample cone, in the effective cone. There's a final wall which I actually will tell you exactly what this is. This actually will always be a particular Kronecker moduli space. Moduli space of Kronecker modules, is that right? Space of Kronecker modules. Alistair sense. Okay. Yeah. So let me start talking a little bit more about stability conditions. But so I guess you've had lectures on this already here, right? But I think I will. Refresh your memory.
So the audience changes every time.
Right. Okay, so I won't. I'll be gentle since I'm by no means an expert myself. So stability condition I could start in general with a general variety, since in fact you could start with a general triangulated category, but let me stick with the general variety. It's going to be a pair consisting of a is the heart. This is the heart of a T structure. On the derived category of coherent sheaves, which means that the objects are going to be some sort of complexes. You can think of them as represented by complexes of sheaves on X. And then Z. Now, in fact, at this point, I think I will make use of, I will choose an ample line bundle, an ample divisor class, just to make things simple. So what I wanted to say is that Z is just a map from a linear map from the K theory of X to C, but I just to fix in our minds what's really going on, let me just assume that Z has the following form. It's going to have real and imaginary parts, and let's just assume, which I won't need to in general, but let's just for this discussion, let's just assume that Z has a nice form. It's going to be given by what's a pair of linear maps, and let's say it just looks like it's given by turn characters of E times complementary product with the complementary power of H, and then followed by BI sum. So this is the real part and the imaginary part. Of course, if I don't have to do this, but this is a nice form for a linear map from the K theory to C, which is probably easier to digest than writing down a general linear form. And of course, they have to satisfy. There's sort of a precondition for stability, which says that Zx of A should be in this upper half plane minus 0 for all objects in A minus 0. And by the upper half plane here, I mean this upper half plane. So I include the negative reals. So that what that means in practice is that the imaginary part is non-negative, and if the imaginary part is 0, then the real part is negative, right?
Why do you write H minus 0?
Because I don't want objects to have 0 charge unless they're the 0 object.
What is H?
Oh, H. Okay, so right. Thank you. I could have dotted in for H. Yeah, you're right. Thank you. So that's sort of the precondition. Then the game is to convert, the slope stability that we all all timers and vector bundle, moduli vector bundles like into this sort of fancy new terminology, which is that you define phi sub x of A for an object in this category to be, I guess, this angle is this arg zx of A, if you want, divided by pi, or I don't know if you think of arg as going from 0 to pi. You think of arg as going from 0 to pi, right? So we divide by pi to get a number going from 0 to 1, and use that to define stability in the usual way. So as like in the last talk, so an object is stable if every sub-object has a smaller arg. And then the actual stability condition is that finite Harder-Nardin Riemann filtrations. Exist. They're unique, of course, once they exist, so they exist for arbitrary elements of A. So I don't want to go into this too much, but that's the usual definition of a stability condition. And then there are sort of a number of examples which we trot out. So, and okay, so far. So the standard examples is the first is ordinary stability for vector bundles, or even coherent sheets, but vector bundles on a curve. So how does that work? So there I'm going to let A be the standard heart of the standard T structure, which is just coherent sheaves on the curve, and Z is just the translation of slope stability into this sort of fancy framework, which just says that I take the minus C1 dot H, and then I guess rank minus C1, and then maybe rank dot H just C0. So this translates into the arg of this, saying that arg of arg of this is less than arg of another is translates into saying that the mu's satisfy the right inequality. Whoops. Now the interesting thing is that ordinary stability in higher dimension is not a stability condition. Ordinary Mumford degree stability, because of the problem that if you use degree stability, if you use just the first Chern class and the rank, then both of these are 0 for sheaves that are supported in codimension 2 or more, and therefore I'd have sheaves of codimension 2 or more mapping to 0, which I don't want to allow here. So there's a completely different sort of example. Which I'll just, for convenience, I'll do this on projective space. This first one was when X was a curve. But essentially, this is the only stability condition on a curve. I'll say what I mean by that in a second. Actually, maybe with the exception of P1. So when X is Pn, you can consider. So suppose I fix OPn of D and I consider the following objects in the derived category of the coherent sheaves on Pn. So this is just O of d minus n shifted by n, O of d minus n plus 1 shifted by n minus 1, and then n of d not shifted at all. This is an exceptional collection of sheaves on Pn, and I think it's called an Ext exceptional collection in the sense that I think there are no, let's see, there are no Homs going that way, there are no Homs going this way, but there are higher Exts going this way. Turns out that if I sort of construct if I look at the category of, it's essentially going to be the category of complexes, but if I look at the category sort of generated by these things and all of their extensions, so I'll call this sort of the Ext generator. This is sort of generated by all extensions. Then this is the heart of a T structure. On the bounded derived category of coherent sheaves on Pn. And furthermore, it's easy now with this, since everything is an extension of these guys, that means that the general object in A just has the invariants of the general object in A are just the positive integer combinations of the invariants of these guys. So if I just send all of these to the upper half plane, then I will have constructed a stability condition. So then if I just let z sub, I don't know, zeta 1 through zeta n be the zeta naught. So if I choose some complex numbers in the upper half plane and I just send as long as I send this, I set this to be zeta I, then these are all stability conditions. And I guess this is the first time that it becomes more plausible that the stability manifold looks like a complex manifold of dimension n plus 1, because this is in fact this is h to the n plus 1. This is a sub. These are all open sets so these define open sets in the stability manifold. The moduli of stable objects would be called, you can associate to the zeta i's, you can associate if you're fixing invariants is the same thing as fixing some integers to attach to each of these. And then the moduli space would be, what would we call it, Alistair? The moduli of quiver representations with relations, or for the quiver with relations associated to projective space. So this is well known and has wall crossings and whatnot. So that's another example. In fact, let me draw a little picture. advertise some work of some colleagues of mine. So if I look at the stability manifold for Pn, I can talk about, let's sort of I'm going to draw it this way. I can talk about the quiver region, or the quivery region. This would be all stability conditions that can be obtained, and I've got to be careful, that can be obtained from any exceptional collection with this nice property, and zeta i's corresponding to the objects in that exceptional collection. And you can do a little bit more. There's a natural action of the complex numbers by tilting on this. I don't think I need the full GL2R plus, but there's and I can sort of extend this by this natural action. This would be sort of the entire region of the stability manifold for projective space, where the moduli problem the moduli space can be described explicitly as a space of stable quiver representations. So that would be, for example, a region within the stability manifold where every wall crossing is explained by geometric invariant theory, and et cetera. So this would be a region that maybe we could say that if we claim that we understand geometric invariant theory and varying parameters well, then we understand all the behavior in here. In the case of P1, everything is quivery, is equal to quiver region. In the case of P2, it's not true. However, and I'm going to draw a picture that'll make this more suggestive. If I fix any Chern character, so remember, if I'm fixing a Chern character for my moduli spaces, then I said before that this will this will give you a collection of walls within the stability manifold. And it turns out that every wall, every chamber intersects. So for each fixed CH naught, every chamber intersects the quiver region. This is a paper by Beyer and McCree. Okay, it's on the local P2, but I think this is the same. This is true also for P2, which means that if you're only interested in moduli spaces, and what are the moduli of Bridgeland-stable objects, then in particular you know that they're all projective, because every moduli space you can. If I have a moduli space associated, well, that'll be Gieseker, but okay. So if I have a moduli space associated to an X, I can follow the chamber into the quiver region and then deduce from the projectivity of moduli for quiver objects that they're projective. I can also, any wall crossing, I can sort of follow the wall into the quiver region and realize the wall crossing is a variation of GIT parameters. So I claim that knowing that the chambers all intersect the quiver region is basically just as good as knowing the quiver region is the whole thing. Incidentally, I guess if you're out here, I'm thinking out here as the moduli of Gieseker stable bundles on P2 with fixed Chern class. And I guess Aaron likes to say this, right? If you following this in here and saying that the moduli of Gieseker stable sheaves is quiver is actually a theorem of Le Potier, basically. I mean, this is sort of equivalent to the theorem of Le Potier at the end of his book on vector bundles, where he describes the moduli of stable bundles on P2 as a moduli space of complexes with, a quiver representation with relations. But all the Bridgeland guys are the same, and I'm going to exploit that. P3. Quiver region. Presumably, it's going to be far away from Giesecke stability. But, all right, Aaron won't like, I don't know if you'll like this, but so there's sort of a path you can trace from the quiver region to P3, maybe a thick path. But this was recently done in work of Bayer, McCree, and Toda. I think this is significant because this says that if you want to, say you wanted to understand moduli of stable bundles on P3, some given invariance, you could start by trying to understand the corresponding quiver representation, and then the hope is that as you follow this path, you're crossing walls, maybe interesting walls, maybe new kinds of walls that we don't understand yet, but where perhaps you can see what happens to your moduli space. That seems a very interesting thing to me. I don't know. This is like these old maps, right, of the old explorers. I don't know. I think here there be dragons or something. I mean, I don't know what on earth is going on as you cross these walls. Are they GIT crossings? Are they? Who knows? That's kind of a mystery right now. But we do know that there's sort of a path in the stability manifold where if you sort of follow it, eventually you will find yourself in the moduli of Giesecke stable objects.
Sorry, but do you know that Giesecke stable objects correspond to some Bridgeland stability condition?
I mean, actually,
For well, no. But what I do know is if I fix the Chern classes, then there will be a chamber in the stability manifold where the objects are moduli of Giesecke stable. That's also a consequence of what you did, right?
Yeah, but I mean, actually, everything outside the query region is still conjectural.
Oh yeah, except, well, you found this path. Right? I mean, you found some actual honest-to-God stability conditions, I think.
I don't think you can
Oh,
prove
shoot.
it outside.
Okay, so it's even worse. Okay. Well, then my answer to
I can say question marks.
then my answer to Bert. Okay, so I'm going to have to sit down with Aaron because I thought that I thought that was a consequence of your codimension 3 Bogomolov inequality. Okay. So this is really unknown territory. It's clearly now unknown to me. Fortunately, I'm talking about P2, not P3. So let me give you a concrete example. So I want to give you another upper half plane. So I want to give you a slice of so what I want to describe here, maybe I'll call this U, is the upper half plane. I want to describe a slice of the stability manifold for an arbitrary surface. Be careful, maybe pre-stability conditions for an arbitrary surface is proof. Let me give you a slice of the stability manifold that was constructed by Bridgeland and that we can, for K3 surfaces and abelian surfaces, and that we now know how to generalize for arbitrary surfaces, in particular P2, which I want to talk about. So the idea is going to be is to somehow deform this. So we didn't just put a dot here to emphasize it's a complex. So we didn't like this. We didn't like Mumford because, well, in particular, it doesn't contain the, it doesn't take into account the second Turing class, right? So it can't possibly define a stability condition. So the idea would be to try to deform this. Now, it turns out that the best way to deform it is actually by first switching real and imaginary parts with a sign. And so bear with me for a second while I write something formal down. Let's see, I'm going to have rank. Okay, so I claim that these are going to be central charges associated with stability conditions. Now, what do I mean? What I mean by the Turing character of E dot twisted by minus s is simply going to be the ith Turing character. Well, what I'm going to mean is I'm going to take the Turing character of E and I'll multiply it by e to the minus sh. The problem is that s might not be an integer or something, so this is not an actual line bundle, but it doesn't matter. This is a formal thing in the ith spot. So this is what the Turing character of e of minus s would be if s were an integer, right? If this was really the twist by minus sh. Okay, so this is. So of course, this is some kind of a deformation. If this t gets very large, I could put the 2 over t squared over here, but it doesn't matter. As t gets very large, this term dominates, and you're essentially at a sort of switching of the Mumford stability. So this should be thought of as t gets very large as converging to Mumford stability. Now, it looks like a strange thing to do because how can I arrange for the first Turing class of something to be always positive? Well, this is this sort of tilting that does this for you. So if I define so I define QS to be sort of the extension closure of all degree stable sheaves of slope bigger than s, and I define Fs to be the extension closure of all degree stable sheaves of slope less than s, and I guess I have to also union torsion sheaves, skyscraper sheaves. Then this category, A sub s, is just what the category of two-term complexes that you would get that would have cohomology in F on the left and in Q on the right. So if I take an object in this full subcategory of coherent sheaves, and I take an x2 of this against an object in here, and that's what the most general object of AS looks like. Again, two-term complexes where the Q appears on the right and the F appears on the left. In Harder-Riemann filtrations, Q appears on the left and F appears on the right, and I guess that's why it's called a tilt. Anyway, this is a heart of a very natural T structure, and see what we've done by putting Q on the right. Well, objects of Q all have positive twisted first Turing class. That was exactly built so objects of Q would have, stable objects of degree bigger than s, of slope bigger than s would have positive first Turing class. Objects of F have twisted first Turing class less than or equal to s, but since I am shifting these objects by 1, that switches all the signs, and so this becomes positive. So this first Chern class of E minus S is positive both for objects in here and all the components that they're built out of and objects in here. On the other hand, if this first Chern class is 0, then either my sheaf was a skyscraper sheaf if it's stable. I'm sorry. Yeah, either it was a skyscraper sheaf if it's stable, but the rank of a skyscraper sheaf, I'm sorry, the CH2 of a skyscraper sheaf is positive. So this is 0, this is positive, so this is then, oops. Did I screw up? Probably.
Negative as it should be.
Yeah, so it's negative, right? Or else, yeah, or else this is I'm in the particular case where I have a vector bundle, a stable vector bundle of slope exactly S, should cause this to be 0. And then the Bogomolov-Giesecker inequality will tell me that this has the right sign after I shift by 1. So it's, and then that'll work for all t. Doesn't it independent? So this rank already has the right sign. It's the negative in sign, and this will have the right sign also. So that'll tell me it's a pre-stability condition. And then the really hard work is actually proving finiteness of Harder-Nernst Riemann filtrations. Okay, so now let me.
You said vector bundle then. I believe you, but
Torsion-free sheaf also. Well, the C1 doesn't matter. The torsion-free sheaf. Bogomolov-Giesecker holds for torsion-free sheaf, stable torsion-free sheaves and vector bundles. So it gets even better when you subtract out. Trust me. Okay. Okay. So now let me go back. Let me draw the picture for P2. So I've got my ST plane, upper half plane of these deformed stability conditions. So as I said, this is in Bridgeland's paper on K3s for K3s. Although there's a little bit of a different argument and a little bit of a better. There's a little bit of a bigger piece of the stability manifold that comes from the fact that you can do a little better than Bogomolov-Giesecker on K3s, or when K is trivial. Actually, you can't do better on the abelian surface, but you can do a little better on K3s. But this works on an arbitrary polarized surface. Okay, so the picture for P2 is going to be the following. I'm going to have. This is this sort of real two-dimensional slice of the stability manifold, and it turns out that I learned this from Arend and Emanuele, that this you can just compute away, and you will find that the quiver region sort of meets this slice in these semicircles. In particular, obviously, this is going to be this semicircle is a semicircle where O minus 2 shifted by 2, O minus 1 shifted by 1, O. So the quiver region meets this, and for this you actually have to act by this C star action on the quiver region to get here. But anyway, the quiver region does meet this. Up here you have Giesecker, moduli, I guess, and then you just crank away. So you fix some Chern classes, and in fact, let me just, in the interest of time, let me fix the Chern classes for the Hilbert scheme for the ideal sheaves, and you can ask sort of, the first question is sort of, where's the first wall? And the answer is the first wall, draw walls in red. The first wall up here reaches from -1 to -n. So that's a wall. What does that wall correspond? Remember, a wall is supposed to correspond to a sub-object of the ideal sheaf that destabilizes, that sort of does not destabilize if you're up here, has the same slope, and then it destabilizes the ideal sheaf when you come down below. And that object, not very surprisingly, is O minus 1. So this innocent-looking exact sequence is which of course can't possibly destabilize the ideal sheaf in any this is multiplication by L, the class of a line, which is, ideal sheaves have rank 1, so in ordinary stability there's no way that they become unstable, but in this Bridgeland stability these particular ideal sheaves become unstable when I cross the wall. I mean, this is just a straight computation. You can compute this charge, you compute the arg, you can compare it with the arg of this, with the arg of the ideal sheaf, and it happens. It's a little bit harder to prove that this is the first wall, but that can be proved also. Of course, what happens when you cross a wall? So that's an advantage maybe we have over in moduli, is that we understand what happens when you cross walls, which is that sequences which become destabilizing get switched, right? So this sheaf is replaced by another sheaf. These sheaves are replaced by other sheaves on the other side of the wall, which look like extensions of O minus 1 by OL minus n in the other direction. So in fact, when you cross this first wall, I advertised that these stability conditions are stability conditions on two-term complexes, but this actually does not create yet a two-term complex at the first wall. Does that make sense? Sort of? Okay. So then you start computing walls and trying with great difficulty to determine rule out walls. So you can check that in fact it's a straightforward computation.
Is minus n the same as minus d?
Yes, thank you. I knew I was going to do that eventually. Where did it go? Where did it happen?
D at the bottom. Should you just put minus n?
Yeah, thank you. Straightforward computation shows that all walls are nested. Are nested semicircles. And so you never encounter, you don't have this, so I don't know how to say this. So this is out. You never see something like this. You never see so if you're sort of traveling in from the Hilbert scheme and you cross a wall, you'll get to a new birational model. You'll never have a choice to find two other birational models. The birational geometer, perhaps that's obvious, but for us, you can do this with a computation. So the walls don't look like this. Instead, they look like something like that. This is what they look like. What else can I say? There appears to be a linear map. So in all there's a linear map as follows. Actually, let me say a little bit of a word. So these are semicircles. Actually, every wall in this slice on any surface is always a semicircle. These are all semicircles with center at some point x and radius x squared minus 2n. So in particular, every point in this left of this vertical line, which actually tells you when the ideal sheaf is, you stop talking about the ideal sheaf when you cross this vertical line. So you want to be over here. Every point in here is on a unique such, whether it's a wall or not, is on a unique such semicircle, which means that I can describe a map. There's a map sort of from the second quadrant so a point in the second quadrant goes to this x, which is the, so I have a point. I draw, there's a unique circle of center x and radius, so x is a point down here. There's going to be a unique circle, so I map to the center of that circle, and then I map to, there's going to be a linear map. I can even tell you what it is. It's like 2x plus 3 or something. I mean, it's not a complicated map. There's a linear map to L of x such that L of x h minus e is the corresponding wall on in the effective cone. So this sort of tells me that morally, at least, there should be a map from this slice of the stability manifold to that ample cone, which is long gone, to that effective cone, which is long gone. So crossing this wall really does correspond to crossing the wall in the effective cone. And I really want, what we really want, which we don't have, is some way of taking a point on this and putting an ample line bundle on the appropriate moduli space, so that that line bundle, for example, is constant on these semicircles, and we understand not a line bundle, but a polarization, and we understand this. We don't know how to do that. But let me show you a kind of a neat consequence of this, which I don't know if the birational geometry people could have come up with. There's this nice theorem of Gaeta, which says that the general ideal sheaf IZ for, Z and P2 of length, and resolves in one of the following way. Resolves either as, so it's going to look like a bunch of that's right, this way. So it's gonna, this one's, so it resolves either this way or it resolves so I don't know how the syzygy people talk about this, but this is true. It has one of the following two types of resolutions. You can both exist, and it's possible for B to be 0, A to be 0, but it has one of the following two resolutions. So what this means is that, in fact, I can tell you what the final wall is. The final wall is going to be the wall that eats the general ideal sheaf, causes it to be unstable, and so the final wall will correspond to either in the first case, it will correspond to a subcomplex that looks like actually any E dot. Shifted by 1. So a sequence like that is actually equivalent. Actually, it gives you is equivalent to a sequence like this. I mean, that's you can always shift the sub and move it over to the right. So it looks either like that, or in the second case, it will look like. Let's see, the OP2 minus k is the odd one out. And then the last thing I wanted to say is that this will give you the final contractions. If this is the last wall, then the contraction is that last contraction is onto this particular Kronecker moduli space. The space of such Homs modulo the GL, the product of the GL actions. So I guess the upshot is that everything seems to be working pretty well for ideal sheaves of points on P2, but we're at C when we're trying to do the higher, the general case, primarily because we don't have any kind of a GIT. We don't know how to construct these moduli of Bridgeland-stable objects in general as in a way that shows that they're evidently projective. So I checked with Toda. He doesn't know how to do it yet either. He moves fast, so I have to always check with him. But no, we don't know how to do it in general. I think it's an interesting problem. I think it's an interesting question. It sort of now tells us that maybe when we want to think of the existence of this stability manifold, says that now maybe instead of thinking about moduli of Giesecke stable sheaves is associated to a fixed Chern class on a surface, that we ought to be thinking about all the birational models that we get in this way at once, and that ought to be sort of the moduli that are associated. So on the other hand, maybe they're not. Maybe they're going to be non-projective, which would also be interesting. So anyway, thanks for your attention.
Questions?
Yes?
What are the special configurations of points that correspond to the...
That's a good question. So if that's an ideal sheaf, well, I mean, so this one maybe is, let's see, is this one the one that's doable? So this should usually correspond to a vector bundle. And so if I dualize the map, I think this would be sections of some kind of very special types of vector bundles. The vanishing locus of sections of very special types of vector bundles on P2. Does that make any sense? I mean, yeah. This happens, I think, first around 12 points, where the last contraction. Yeah, there's some twist of the tangent bundle, and there'll be configurations of points that are zero loci of sections of some kind of twist that show up, that form a divisor and 12 points on P2 or something. I don't know the answer in the general cases, though. It's like this one I don't understand yet. This one's sort of mysterious to me. This happens already with 7 points. I don't know what. Well, no, this last one, this for 7 points is a contraction, so I don't know. I don't know the answer to that. That's one of the things we're trying to figure out, actually, is what. So, you know, a lot of these, the first many walls until you get to a fair number of points on P2, you can understand exactly by points on a conic, points on a line, etc. But then, yeah, then these more mysterious things do show up. So, and actually, if you try to do a similar thing for K3s, they show up immediately. In fact, the first wall for K3s is, I believe, configurations of points that are zeros of sections of interesting vector bundles on the K3. So.
The contractions you're getting, they can be divisorial, can they be?
Yeah, the last one can be divisorial, sure.
Yeah, so they can be a bit of the same dimension there.
Yeah.
Yeah,
Yeah.
birational.
The divisorial when A or B is 0, I think, in this picture, yeah. Well, and a few extra cases.
Any more questions? Okay, so can we head down again?